All right, let's talk about something that's absolutely fundamental to chemistry and physics, the atomic orbital. Now, I know, it's a concept most of us probably ran into back in science class. But what if I told you that top scientists are still, fiercely debating what an orbital actually is? Yeah, seriously. Let's dive in.
So get this. On one hand, you have a 1999 article in the super prestigious journal Science, where researchers claim they actually imaged electron orbitals. Seen them. But then, on the other hand, you have an article from the Journal of Chemical Education that just flatly states there are no such things as orbitals. So what is going on? How can two of the most respected journals in science say the exact opposite thing? That's the mystery we're going to try to solve.
To get to the bottom of this orbital enigma, we kind of have to think like detectives. So we're going to start by investigating the big question right at the heart of all this confusion.
This is really it. This is our guiding question. Are orbitals real physical things that we can actually see? Or are they just imaginary ideas? The answer, it turns out, is way more fascinating than you might think, and it tells us a whole lot about how science really works.
To find the right answer, we first have to figure out where we're going wrong. And usually the confusion starts with two really common but pretty incomplete ideas that we all get taught from textbooks. So let's look at the two main suspects in our orbital enigma.
So on one side, you've got the idea that an orbital is a physical container, like a fuzzy cloud or a little box where an electron just kind of lives. And that feels pretty intuitive, right? But it's maybe a little too real. Then on the other side, it's described as just a bunch of complex math, a function with no physical meaning at all. And that one, well, that feels way too abstract, totally disconnected from the real world.
And this, right here, is the problem. This is the whole issue. We're stuck between these two extremes. One tries to make a quantum idea into a simple little object, and the other just reduces it all to pure math. This split is the very source of the entire scientific argument.
Okay, so if both of those common ideas are flawed, what's the alternative? The big breakthrough comes when you realize we need a third way to think about this. Not about a place or a formula, but about a state.
What if an orbital is neither a physical box nor just some meaningless equation? What if it's something else entirely?
And here it is. This is the answer. An orbital is a model that describes the state of an electron. The two key words here are state and model. It's not the electron itself, and it's not the space it's flying around in. It's a scientific model that describes its properties, like its energy, its momentum, all within the rules of quantum theory.
Here is just a fantastic analogy that makes this so much clearer. Think of an empty orbital like the state of angry in a person who's totally calm. That person has the potential to be angry. The state of anger exists for them as a possibility, right? But it's not like there's a physical box labeled anger inside them waiting to be filled. An empty orbital is the exact same idea. It's the potential state an electron could be in, not a real empty container waiting for one. Let's just break that down a little more. A person's mood is a state, right? It's not a place. And some event, like say you stub your toe, can instantly change that state from calm to angry. Well, in the exact same way, an electron's orbital is its state. An interaction, like the electron absorbing some light, can change that state, bumping it to a totally different orbital. See? It's not a container, it's a condition.
So, if an orbital is a model of an electron's state, what exactly does that model describe? Well, the answer comes down to just 4 key values. We call them the quantum numbers.
These 4 numbers basically give a complete address for an electron's state. First, you have n, which tells us the main energy level. You can just think of it as the orbital's size. Then there's L, which defines its shape. After that, M describes its orientation, its angle in space. And finally, S tells us about its spin, which is a purely quantum thing we can just imagine as being either up or down. Put them all together, and you get a unique ID for the state of any electron in an atom.
Okay, so I think we've cracked the case. An orbital isn't a place or a formula. It's a model of a state. But why is it so important to get that distinction right? Why does it matter?
I mean, who cares if we think of it as a fuzzy cloud or a set of properties? Well, the answer has 2 really big parts. One is super practical, and the other is, well, it's actually pretty deep.
First, on a technical level, this model is an incredibly powerful tool for predicting things. It's what lets chemists understand how atoms form bonds and predict the 3D shapes of molecules, and that's the foundation for everything from new medicines to new materials. But maybe even more important is the second reason. Getting this right is formative. It's our gateway into the really strange, non-intuitive quantum world. It forces us to move past that simple, old-school idea of the world being made of tiny little billiard balls.
So the really crucial takeaway here is this. The whole debate about orbitals teaches us something profound about what science is. Science isn't just about collecting a big catalog of absolute facts. It's a process. It's about building and testing and refining models that give us better and better ways to describe how the universe actually works. And the orbitals, it's one of the most successful models we've ever created.
And that leaves us with a final thought to chew on. Recognizing the difference between reality itself and our models of reality, that's one of the biggest leaps in modern thinking. It allows for nuance, for progress, and for a much, much deeper understanding of the world. So the next time you look at a scientific diagram, ask yourself, am I seeing reality or am I seeing a brilliant model of it? Thanks for digging into this with me.